Hello friends, welcome to the today's session. Today we are going to study one of the important topic in the unit number first, simple stresses and strain. The topic name is temperature stresses. Up till now we have studied that the stresses are developed into the body because of there is a external forces or external loading is acting onto the any particular member or body. So there are body may be expand or body may be a contraction has been happened into the body. So in this particular topic, the temperature stresses means there is a changes or deformation is produced or induced into the body because of there is a variation of the temperature. As the temperature rises, the body will expand, and the temperature falling down, at the time body will contract its shape. So today we'll see that whenever there is a whenever there is a variation of the temperature, free expansion is taken place. At that time, what will the effect of the temperature stresses? And in another condition, whenever there is a expansion is prevented partly or fully, at that time, what type of temperature stresses are induced into the body? In this particular session, we will study in detail. So stresses due to change in the temperature. Every material we know expands when temperature rises, and material contracts when temperature falls. Means there is a rising of the temperature and there is a falling of the temperature. It directly affect to the deformation, or there is a shape and changes into the body. It is established experimentally that the change in the length delta is directly proportional to the length of the member L and change in the temperature T. So this delta is nothing but the change in the length, and it is directly proportional to the change in the temperature and the change in the length of that particular member. So this particular expression is very much important for finding out the temperature stresses. So if you want to finding out because of the rising or falling of the temperature, there is a change in the there is a changes into the body, or changes in the length of the body at that time. So this delta is the change in the length. Original length is capital L. So this delta is equal to alpha TL. So here alpha, it is taken as a coefficient of proportionality. It is a constant. This constant is also known as coefficient of thermal expansion. So T is the small t is the change in the temperature. So the expression becomes delta is equal to alpha TL. So this constant of proportionality alpha is also called as coefficient of thermal expansion, and it is defined as the change in the unit length of material due to unit change in the temperature. So these are the some of the material which has a coefficient of thermal expansions are uh, given here. So coefficient of thermal expansion for some of the engineering commonly used engineering material like a steel, copper, stainless steel, brass, bronze, aluminium. So coefficient of thermal expansions are here. So you remember, please remember these values of coefficient of thermal expansion. After that, temperature stresses. So now our main objective is to finding out the temperature stresses. Actually there are two cases that exist here. One case is the free expansion. When there is a free expansion is allowed into the member or into the material, at that time there is a no stresses develop into the member. If the changes due to temperature are permitted freely, or if it is expansion is permitted freely, there is no stresses develop into the member. So that is in the case of bar as shown in figure below. If the expansion of the member is freely permitted, there is no temperature stresses are induced into the material. You can see into this particular figure the original length of the bar is capital L, and there are changes are happened into the body, and there is expansion has been taken place here alpha TL, because of the free expansion is permitted uh, due to variation in the temperature. So this particular there is a no support condition exist here, so there is only one support is at one end. So that's why this particular member will expand into this particular direction, and the expansion or there is a change in the length, it is alpha T into L. So this particular value, if you want to calculate that how much expansion has been taken place, so that delta value is there is equal to alpha into T into L. So by using this formula you can calculate the total expansion to this particular bar. Next case is the free expansion is prevented partially. So in this figure you can see this, that this particular bar is there, but there is a support conditions are exist on both of these ends. So total length is L, and if it is that expansion is allowed, then we know that there is a change in the expansion is alpha TL, we can calculate. But if it is that there is a support, compressive forces are acting onto the both of the support at that time, so there is a no there is a free expansion is prevented. So there will not be any free expansion because of this support reactions at the two end of this bar. So because of that, there are stresses are developed or stresses are induced into the member because of that support forces P. So on both of these, there are support forces are there, P, and in other capital R is equal to P. So because of that, the temperature stresses are developed. Since the support is not permitting it, the support force P develops to keep it at the original position. The magnitude of this force is such that contraction is equal to free expansion. Because of that support, there is a contraction and there is a expansion is equal here. This support force P is such that it causes shortening of the bar. Because of this support, it is compressive in nature. That's why there is a bar will contract, or there is a shortening of the change in the length of the bar, so that it is equal to alpha TL. So because of the compressive nature of the forces are acting onto this particular bar. So if you want to finding out, though it is that support conditions or support reactions are exist or at the two end, so we have this relation delta is equal to alpha T L. So we know the delta is equal to PL upon A, because earlier we have derived in the earlier lectures PL divided by A, that is a change in the length. This particular formula is equal to alpha TL. So if you simplify this particular equation, so you will get that sigma value. So sigma is nothing but the P upon L. So we will get that sigma is equal to capital E alpha into T. E is the modulus of elasticity. Alpha is the there is a constant of proportionality or coefficient of thermal expansion, and T is the change in the temperature. So which is the temperature stress, this particular value. By using that, you can determine the temperature stresses because of the compressive type of the forces are acting on both the ends. So this sigma is the temperature stress. Because of that, body or member has prevented expansion. Free expansion is prevented by providing the support at the two ends. Yielding at support. So if free expansion or yielding at support is prevented partly, as in the case of member as shown in this particular figure. So you can see this in the figure, there is a bar is there, uniform cross sectional bar. So there is a support is there at this particular end, and there's the original length is capital L, and there is a support is provided by the delta, uh, by this particular delta of length, and the force developed corresponding to the amount of free expansion is prevented. So the shortening caused by support reaction P. So in this particular case, there is a free expansion has been taken place. So the original length of the bar is L, and the free expansion as usual that alpha into T into L. So this particular free end is there, and the expansion is prevented by developing a compressive force P. So because of this, support is at a distance of delta. So there is a free expansion is taken place only delta of length. So beyond that support, so there will not be any allowed of the free expansion. So that's why the whatever the expansion is prevented by the development of this compressive force at support, we can calculate by using this relation. So expansion prevented means the total expansion has been allowed, it is alpha TL and minus delta. So this delta expansion is allowed only up to this particular support. If you subtract from the total expansion, you will get the expansion prevented. So this particular amount is prevented because of this provided support. So putting that value of delta here, delta is equal to PL upon AE, and alpha TL is there, alpha TL minus delta. So if you subtract this delta to this total expansion, you will get the prevention of that expansion prevented because of this support. So if you simplify this equation, so you will get that final sigma value again. So again, sigma is nothing but the P upon A, load divided by cross-sectional area of the bar. So sigma is equal to E in bracket alpha TL minus delta divided by L. So where sigma is the temperature stresses developed into the bar, E is the modulus of elasticity, alpha is the coefficient of thermal expansion, T is the change in the temperature, whether it is the rise of the temperature or falling of the temperature, L is the original length of the bar, delta is the there is a distance between the original length and the support. So there is a this particular length is delta, and L original length of the bar. So from this particular expression, whenever there is a yielding at support is there, at that time, because of the support, there is a that amount of the expansion is prevented by providing the support at the two ends. So this particular support by the for the partly whatever the expansion is prevented partly. So by using this relation, we can easily calculate the temperature stresses. In the previous derivation, so there is a expansion is fully prevented, and here the expansion is partly prevented. If it is expansion is partly prevented, at that time how much expansion is prevented, so that value you can determine by using this relation. So you just be you remember this particular expression whenever the expansion is partly prevented because of the support condition. So we can use this formula to finding out the whatever the temperature stresses are developed within the bar. So for this, that's it for the this particular presentation. In the next presentation, we will look at to the whatever the problems are there for finding out the temperature stresses. Thank you very much.